Let's jump into several examples with regards to kind of fluids and pressure and densities. Okay, so here's the first one. So we have a hose which is 1.5 meters above the ground and it's parallel to it. The pressure in the hose is 3.8 times 10 to the 6. Okay, so 3.8, I guess, megapascals. Water is moving through the hose at a speed of 12 meters per second. If the end of the hose is 18 meters above the ground and open to the atmosphere, so that means the pressure is 1 atm, as they tell us, then what is the speed of the water coming out of the hose, okay, at the top? And then hint, use Bernoulli's equation. All right, so let's try to break this down. So what I'm going to try to do is kind of first visualize this whole thing. So we have some particular, okay, so let me just kind of draw it out in here. So we have right here an actual kind of hose, and that particular hose when duplicated, and then there's, it kind of connects back and it's much higher, okay, above there. So this hose, okay, is 1.5 meters. So, your height here is 1.5, I'm going to call this 1 meters above the ground. Now, it has a certain pressure. So this pressure inside of it is 3.8 times 10 to the 6, okay, or just megapascals, okay. I'll write that so I don't have to write the actual scientific notation. Now, the speed, okay, so that means that the flow, okay, of the water in here is at a speed of 12 meters per second. All right, so that's what we have there. Now, if it's water, that means the density, now we should know the density of water is 1,000 kilograms per meter cubed. Whenever it is not given, and that's what you should assume, okay, or 1 gram per centimeters cubed. So we have our density. And that density obviously will stay the same throughout. So now what it wants to know is the following. So we have this hose which continues, I guess, upwards, right? So maybe, it kind of connects back, so it goes kind of like this, maybe something like this. And now this thing is 18 meters above the ground. So here I'm going to call this H2, 18 meters above the ground. Now, we know that it's open to the atmosphere, so that means, so right here, so the actual water's coming out, and if it's open basically to the air, then we will have that indeed the pressure, okay, in here is going to be 1 atmospheric. So now please recall 1 atmospheric. I'm changing everything to kind of metric standard units. So this is going to be pascals, okay, so that is equal to 1 atmosphere. And you can double check that for yourself, but that's what it would be. Now, we want to be able to know what the speed is, right? So what is this speed, okay, which is coming out of the hose? Now, we have all of this information. Well, so from Bernoulli's equation, so if you set this up, I'm going to divide this in half, all right? So kind of on the left-hand side, so call this 1, okay, and that's going to be this hose. And then on the right-hand side, let's call this 2, and that's going to be all the way at the top. All right, so that's what we have there. Now, what Bernoulli's equation tells us is that the pressure that is present plus 1/2 of the density V squared, that's kind of the kinetic energy component, okay, within here, plus the actual, this is the gravitational potential energy component, okay, so the density times g, okay, times whatever height it is. I'm going to start labeling these. So this is 1, okay, the speed is 1, the density is going to be the same. Now, this is always constant by Bernoulli's equation. So it's basically constant, and it comes out from the law of conservation, right? So you can kind of break this down, and that's what we will get. So if this is constant, I'm going to duplicate this back in here. That means that the left-hand side and the right-hand side are going to be equal. Okay, so now the only thing I'm going to remove right here, and I'm going to put here, this is pressure 2, speed 2, and then this is height 2. And these two are equal to each other, right? So these are supposed to be equal to each other. Now on the left hand side, I pretty much have everything given to me. So if I substitute this back in here, so notice, so 3.8, I'm going to change this back in. So this is going to be pascals, plus this is going to be 1/2 times the density, so 1,000, okay, times the speed, which was 12 meters per second squared, and then plus, okay, again, so the density itself times gravity, and then times the height, which is 1.5 meters above the ground. So we have all of this given. Now I can compute this. So I'm going to put this in my calculator and then just get an answer. Guess I'll do that quickly. All right, so there you have it. Okay, so that's the left-hand side. Now, the right-hand side, so what I will have is, I do have the pressure, right? So this is 101,325. So I have the pressure. Now, I also have this. Okay, so I'm gonna actually put that in here because it's known, 9.8, and then the height was 18. So really the only thing that I don't have is the speed. So everything else I do have. So this is going to be v2 squared, which is that speed we're looking for. So again, so I can, add these two together, okay, right here. So I'm going to find out what that is. I'll get an answer. And then, we're going to try to solve for v2. All right, so there you have it. Okay, so now because these two sides are equal, so these are equivalent to each other, then what I can do is, I can bring this over to the other side. All right, so let's, do that. So if I take these numbers within here, so let me take 3886700 minus 277725. All right, so that's now on the left-hand side there. Okay, so this is what I would have. And this would have been divided by, so now notice I'm going to take this answer and I'm going to divide this by 500, okay, because I want to be able to solve. So this divided by 500, okay, is that. And now I want to take the square root because I want to be able to find out, okay, what that V2 is. Okay, so ultimately this is what I'm after. So if I take this and I take the square root of all of this, okay, so if I take this answer, I'm going to use kind of exponents, okay, to the 0.5, which is the square root. So it's going to give me exactly what that speed is. So V2 is going to be about, and I guess within here, it's going to be approximately, so 8495, etc. So I'll just put it to 85 meters per second. Now you can round it to whatever it is that you like, okay, so within here. So that would have been the answer. Notice it's, it's definitely pretty quick. It's coming in at 12 meters per second and then it's coming out at 85 meters per second as you're going through there. So that would have been the answer, okay, so within this one. And that is pretty much it. So we can use Bernoulli's equation in order to be able to find out what that answer would be. All right, so that's the first one. Here's another example. It says an airway in a medical device is opened by lifting up a small gap. All right, so see the figure. So here it's kind of opened up, and so there's going to be some flow of liquid in here. So find the speed of the fluid coming out of the gap if the speed on top of the fluid is initially at 0 meters per second. So that means all the way up here. Okay, so this is the initial speed. It is basically 0 meters per second. Okay, so that's what we have here. Now it tells us, okay, so that H1 is 45 centimeters. So this is 45 centimeters. H2 right there is only 15 centimeters, okay, right there. So notice that the difference, okay, in height, so 45 minus 15, so this would have been 30 centimeters or 0.3 of a meter, right? So that's what we would have had over here. Now, assume air surrounds the device and fluid. So now this is crucial information because that means all over here, okay, so although this is lifting, okay, so as you're going through here, so all over here, it's just air. And if it's just air, that means that the pressure at all of these points. So this is going to be kind of at the atmospheric pressure over here, and it's going to be at the atmospheric pressure over here. And so you can think back again in terms of Bernoulli's equation, and you can set this up. You have the same pressure, so the pressures will actually cancel each other off. And you can solve for what the actual speed will be. Okay, so within here. Now, this is, okay, something that we actually know in fluid dynamics. So Torricelli's kind of equation, which we can put up here, which basically tells us if it's open to the atmosphere, so meaning the pressures here are identical, right, within here, you have, so obviously the densities are not changing or anything like that. So really the only thing that plays a role, okay, is the speed. So the initial speed, which is 0, and then our final speed, okay, right here. And obviously the heights change, okay, so within there. And within this equation, so you may recall this, and I encourage you to kind of look up Torricelli's. Maybe I'll put up a link up above there for you, okay, to get refreshed. So that means that V, okay, squared is actually going to be equal to the initial speed plus 2 multiplied by, so this has to do with gravity, and then the change in height. And this is very much kind of from kinematics, okay, if you recall all the way back. So within here, or, you know, in terms of the law of conservation, if you're solving for speed. So with this information, we have everything. So this is really 0. Okay, so it's very simple. So 2 times 9.8, the height difference is 0.3. Okay, so this makes it super easy to be able to solve. So let's take out the calculator. So 2 times 9.8 times 0.3. So this is just simply 5.88, and this is going to be now taking the square root of that, right? So if you take the square root of it, well, then what you're going to get is that the speed within here is 2.42 meters per second, okay? And again, you can round to whatever it is that you like. I guess, well, the 0, we always assume that it has infinite sig figs, so it looks like it's 2 significant figures between the heights. So, you know, you can certainly keep that, or you can round to what it is. So that is actually it. There's really nothing else in terms of this fluid that we would have to consider. Okay, so that's another example for you. Here's the last example of this video. All right, so we have this, which basically is Poiseuille's law. Okay, so within here, so this is a pretty neat equation and a very powerful equation. And it says if all variables remain constant, but the radius, okay, is reduced by 25%. All right, so it's 75% of what it used to be. Then what impact would be caused on the volume flow, right? So what would be the volume flow in comparison to the original amount? Well, since we don't have any numbers, you know, so students typically will struggle with this, but please recall, so your initial, right, so this is your initial volume flow rate, is equal to this, you know, times pi r over 4 divided by 8 eta, okay, times the length. Again, this is the length of the pipe, so it has to do with the volume flow rate through a pipe when there's a pressure change. Okay, so that's what is happening here. So this is with regards to Poiseuille's law. And I can put up a link to Poiseuille's law as well for you if you want to see a little bit more. So for this, if this is initially, what they're telling us is that everything is constant. So, you know, this stays constant, obviously pi stays constant. Okay, 8 will stay constant, eta, and then the length will stay constant. And the only thing that's changing is this. So that means that the final kind of volume flow rate would have the same, okay, pressure change. So this is still going to be that. It's still going to be divided by 8, you know, eta L. And the only thing that changes, and maybe I'll do the change in color, is going to be that we have a 25% reduction in the radius, which means, so 25% is 0.75, okay, of the original radius that we have, okay, within here, and it's to the 4. Everything else stays the same. Now notice what happens in here. So this is a great question because it will kind of tickle your intuition. So 4, if you bring it in, if you know your exponent rules, so this is going to now give you the following. It's going to be delta p pi So now this, of course, I'm going to bring that to the front, all right, just so that you can see, okay, what the power will be here. So I'm going to bring that 0.75 to the 4 in front. And then everything else, notice R, this is still going to be to the 4, divided by 8 eta L. Well, okay, so if you look at this, so this right here that you have is basically the same thing, right? This is just your initial flow rate, okay, that you've had in here. So if you wanted to say this is your initial flow rate right here, and how did it change? It just changed by this factor right there. So now, you know, let's take that into a calculator, 0.75 to the 4, and this is what we're going to get. So that means that the final volume flow rate is equal to 0.3164, etc., multiplied by the initial volume flow rate. So if you're looking at this, what has the reduction caused? Okay, so if you see this and if you put this as a percent, this is about 31.64%. I'm not going to be rounding anything here. So if the actual radius is reduced by only 25%, the volume flow rate, okay, drops to only 31% of the original, which means it has dropped by nearly 70%, right? So, you know, nearly 70%, okay? So, you know, approximately 70%, about 68.36, I guess, okay? So approximately 70% drop in volume flow rate caused by only a 25% decrease in the radius. This is really substantial, okay, to think about. And, you know, what Poiseuille's law is really good for is to actually let us know. So if you do have kind of cylindrical-like pipes, you know, even if you're thinking about, you know, the human body, and you have a reduction, okay, anywhere, somewhere along the line of your actual pipe or tubes or arteries or anything, it's going to have a big impact on the volume flow rate, okay, that is caused. So that's this particular example. So to answer it, you know, if everything stays the same, then what impact would be caused to the volume flow rate? Well, the impact is about a 70% drop in volume flow rate. That's what this would be. Now, what would be the volume flow rate in comparison to the original? Well, in comparison to the original, it is about, you know, 0.3164 of the original, or it's only 31.64% of that original volume flow rate. Fantastic question, okay, for yourself to be able to understand, okay, the impact of radius reduction. All right, so that is it for this video and for this question, okay? So thanks for watching. Hopefully we'll see you in future videos. Bye, everybody.